All right, so we just talked about radioactivity and alpha and beta decays and processes by which unstable isotopes or unstable nuclides, um, the processes they undergo, alpha and beta decay, to try to make a more stable nucleus. We talked about that after a certain amount of time that an unstable nucleus or a radioactive nucleus will break apart and make a daughter nuclide and typically another particle, an alpha or beta particle. In this section, we're going to talk about half-life, and half-life gives us a measure of the amount of time a radioactive species exists before it breaks apart into a daughter nuclide, or it goes through that process. Okay, so half-life is denoted as T subscript 1/2. So a lot of times you see it like T 1/2, something like that. That just means half-life, and that implies we're dealing with a radioactive system, and that's the amount of time it actually takes for half of the amount of the radioactive species we have to decay into its daughter. Okay, so for example, if you start with 100 grams of a radioactive isotope, and we wait the time that the half-life is, we'll have 50 grams of that material left. So 50 grams of it will have decayed away, and 50 grams of it will still be remaining. So the half-life is the time it takes for half of the radioactive isotope to go through its decay process. Okay, and the nice thing about half-life of radioactive systems is it's really not affected by nature. I mean, it's not affected by temperature or pressure or any of that. It's a pretty set process that just naturally occurs in that amount of time. Okay, so if we start with radon 222, which is one we looked at last section, and it goes through an alpha decay process, we can see that radon is the parent nuclide. It's the one we're starting with, and when it goes through its process, it goes to polonium 218. It emits an alpha particle. And remember, the alpha particles are symbolized by that. Alpha particles have 2 protons and 2 neutrons in them. So their atomic number is 2 and their mass number is 4. Okay. The half-life of radon 222 is 3.82 days. So not quite 4 days, but a bit over 3.5 days. So that means if I start with a certain amount of radon, after 3.82 days, only half of that will be remaining, and half of it will have decayed into polonium 218. Okay, and if we wait another 3.82 days, we'll only have 25% left, because we had 50% left after one half-life. If we wait a second half-life, then we'll only have 25% left, because that's half of what 50 is. Right, so we kind of made it. There's a little chart here that's dealing with half-life. On the vertical axis, we have the amount of the radioisotope that we have at any given time, and along the x-axis or the horizontal axis, we have the number of half-lives. So if we initially start with 100%, or you could do 100 grams of your radioisotope, after one half-life, 50% or 50 grams of it will remain. Right, half of it is decayed away after a half-life. So if we start there, we have 50% or 50 grams. After another half-life, we're now down to 25. Okay. After 2 half-lives, we have 25% of what we started with still remaining. The rest of it has gone through radioactive process and decayed. If we go 3 half-lives, if we wait 3 half-lives, we're now down to 12.5% of the amount of material that we started with is still there. Okay, if we wait a fourth half-life, we're down to 6.25% left. Okay, so you can see that each half-life we just divide the amount by 2. So we start with 100%. After one half-life, we have 50%. After another half-life, we divide 50 by 2 and we get 25%. After a third half-life, divide 25 by 2 and we get 12.5% left. After 4 half-lives, we're going to take 12.5 and divide it by 2. And after 4 half-lives, we have 6.25 or 6.25% of whatever we started with left. Okay, and that just keeps going. And after each half-life, we divide what we started with by 2, and that's our new amount that's left. This is a table that's in your book. It's kind of nice. It gives you some measure of half-lives, and you can see that some half-lives are really long, like uranium-238 has a half-life that is 4 trillion years. 4 billion years. Sorry, can't read my numbers. 4 billion years. Okay, so if I start with 100 grams of uranium-238 today, in 4 billion years, I will have 50 grams of it left, because 50 grams of it will have decayed. And actually, it goes through an alpha process, so it loses an alpha particle. Some of these other ones are a lot shorter, like technetium-99M. We'll talk about the M here in a second. Technetium-99M is used in a lot of different medical system or medical. It has many medical uses. It is used for imaging. It's used for treatment. It's a very common radioactive element to use. Okay, and then we've got other ones. If you look at some of the ones that we saw in the table of nuclides that we looked at earlier, some half-lives are really short, like fractions of a second. Some half-lives are really long, like billions of years. Most of them lie in between. And when we're choosing elements that we're going to use for medical purposes, there's a lot of things that go into that. One, half-life is definitely important, but the type of emission that it has, how it radioactively decays, the energy of the particles that it produces, right? Because we want to be able to balance off the damage that the radiation is doing to your body with the good that it's doing also. So if it's for imaging, then we're trying to figure out if something's wrong with you. And if we have to use a radioactive tracer, then we want to use one that's going to do minimal damage while it's inside of you, right? Or if we're using it as a treatment for cancer, we want something that's actually going to do some damage to the cell, to the cancer cells. So there's this weird balance between the good effects and the bad effects. All right, so a couple practice questions dealing with half-life. So let's pause. You can read through these, try to do them yourself, and if you get them done or if you're struggling with them, come back and watch me work through them a little bit. All right, so hopefully you've worked through these a little bit, but let's take a look at these. Technetium-99M is often used in medical imaging. We just talked about that. The half-life is 6 hours. So if a lab produces 100 grams of this material, because it's not available in nature anymore, so we have to produce it in the lab. So let's say we produce 100 grams of technetium-99M. How much remains after 2 full days? Well, if we're talking about full days, each day is 24 hours, right? And if we're doing 2 full days, that means we have 48 hours we want to determine how much technetium 99M is left after 48 hours if we start with 100 grams, right? So I'm going to start with 100 grams. After 6 hours, that's a half-life, there's 50 grams left, right? Because a half-life means that's how long it takes half of it to decay away. Okay? After 6 hours, there's 50 grams. If I do another 6 hours, there's going to be 25 grams left. So after 12 hours, there's 25 grams left of the 100 grams I started with. After another 6 hours, there's 12.5 grams left. If I do another 6 hours, there is 6.25 grams left. So after one full day, 24 hours, I have 6.25 grams left. Okay, let's start our second day. I'm going to grab a calculator here so I can do this right. So I've got 6.25, and I go another 6 hours. That means I have to divide that again by 2. I have 3.125 grams left. After six more hours, I have 1.5625 grams left. I'm obviously neglecting significant figures, but I just want to show you the whole process. So 6, that's 24, plus another 12 is 36. So we have 2 more of these to do. After 6 more hours, I have 0.78125 grams of the technetium 99M left, and 1 more, and that'll give us 2 full days, 48 hours. 0.390625. Okay, so technetium 99M has a half-life of 6 hours. So if I start with 100 grams of the material, after 48 hours, there's less than half a gram left. At each step, we lose 50% of what we have remaining. So 100 grams to 50 grams to 25 grams to 12.5 grams to 6.25 grams. That is 1 day right there. And then our second day, we go from 6.25 grams to 0.39 grams. Okay, so you can see if the half-life is kind of short, like 6 hours, it decays. And there's benefits and negatives to this. The negative is that if you're using technetium as your in your medical procedure, you need to get or make it fairly fresh, or get it made within kind of the day, or else it loses its efficiency. Also, the good side of that, however, if we're putting that in our body, after a pretty short amount of time, a couple days, most of it is gone. All right, question 2. Cerium-141 is a radioactive isotope that is used for both medical diagnosis and treatment. It undergoes beta decay, so that means it produces beta particles when it decays, and it has a half-life of 32.5 days. Okay. So if we start, now it says we start with a 320 gram sample of cerium-141, and we purchased a while ago. The sample was tested and was found to contain only 5 grams of cerium-141. So we start with 320 grams, and now there's only 5 left. So we want to figure out how long ago the material was purchased. So we start with 320 grams, and we go through one half-life, which is 32.5 days. And with D. After 32.5 days, half of what we started with is gone. So 320 divided by 2 is 160 grams. So after 32.5 days, we only have 160 grams of what we started with left. If we wait another 32.5 days, we lose another half, so 80 grams. We wait another 32.5 days. We go down to 40 left. Okay, so we start with 320 grams, and after 3 half-lives, about almost 100 days, we have 40 grams left. Okay, let's keep going. After another half-life, after another 32.5 days, 40 grams now becomes 20 grams. Okay, go through another half-life. We got to get down to 5 grams. If we go through another half-life, 32.5 grams, 32.5 days, sorry, we go down to 10 grams. And one more half-life, 32.5 days, will give us 5 grams. Okay, so we can see just going half-life and losing half of what we have in each step, each half-life. We can see we get down to 5 grams, and it took us 1, 2, 3, 4, 5, 6 half-lives. So if I take 32.5 days and multiply by 6, I get 0, 3, 12, 15, 1, 18, 195 days. So let me make sure that's right. 32.5 times 6 is 195. So 195 days. So if we started with 320 grams and we only have 5 grams left, we must have gotten that material 195 days ago. Okay, went through 6 half-lives, which means at each step it loses 50% of what it had. In 6 steps, we lose. Well, what do? We go down to 50%, 25%, 12.5%, 6.25%, 3.125%, and 1.5625% left. All right. So that's how you do these. If you got this, great. If you're struggling with this, please either come to office hours or find the time to meet with me.